Chapter 11, Properties of Solutions. Our outline is solutions and concentration units, solutions and concentration equations, actually, factors affecting solubility, colligative properties. Solutions and concentration equations. Many substances we encounter in everyday life are mixtures, such as seawater, soda, milk, gasoline, rocks. When they are homogeneous mixtures, they are solutions. They are the same throughout. So, a solution is a homogeneous mixture of solute and a solvent. The solution has the same composition throughout. A common solution in a chemistry lab is one prepared by dissolving a solid solute in a liquid solvent, but we are not limited to a solid in a liquid. So here's some examples of different solutions. We can have a solute in a gas solute in a gas solvent. The type of solution is a gas. An example of that is air. Remember that the solute is the smaller amount of the two. The solvent is the main component. Another example is a gas dissolved in a liquid. That would make for a liquid type of solution. An example of that is carbonated water. We can have a liquid in a liquid type solution, making for a liquid one. An example of that is whiskey, that is ethanol in mainly water with a little flavoring. We can have ethanol in gasoline. That's a liquid type solution. We can have a solid dissolved in a liquid. So type of solution would say a liquid one. That would be, for example, sodium chloride dissolved in water, or maybe sugar dissolved in water. We can have a solid with a solid type of solution. An example of that would be brass or bronze. Those two involve mainly copper with some zinc in the case of brass, or tin in the case of bronze, as well as some other metals. Solutions can be concentrated or dilute, and we can express the concentration of a solution using, in this chapter, these different types of quantities. There is molarity. We have seen that and used that quite a bit already. The equation for molarity is moles of solute per liter of solution. The unit is the molar, capital M, or we could say moles per liter. It turns out it's temperature dependent because the volume of the solution is temperature dependent. The moles of the solute, no, that's not dependent on temperature, but the volume is. As we heat a volume, it expands. The molality is a new way of expressing concentration, and that is equal to the moles of the solute divided by the kilograms of the solvent. Its unit are the molal, little m, or we could say moles per kilogram. It is independent of temperature because moles don't depend on that, nor does mass. Mole fraction is another way to express the concentration, where the mole fraction of A, let's say that we have a mixture made of A and B. The mole fraction with respect to A would be the moles of A divided by the total moles. So N sub A divided by N sub A plus N sub B. The mole fraction of B would be 1 minus the mole fraction of A. It is unitless because we have moles canceling out. Moles don't depend upon temperature, so it is temperature independent. The last quantity that we talk about is the mass percent. A lot like the mole fraction, except that it involves masses and we multiply by 100. So the mass percent of that component A would be M sub A divided by the total mass, that is M sub A divided by M sub A plus M sub B, and then times 100 for percent. Mass cancels out, so it is unitless. Mass does not depend upon temperature, so it is temperature independent. The mass of the B component would be 100 minus the mass of A. So here's some examples. 1.00 liters of 0.200 molar K2CR2O7 must be prepared. How many grams of the solute are needed? So we take that volume, multiply it by the molarity. We see liters cancel out. And then we get to grams by determining the molar mass of the potassium dichromate, which is 294.20 grams per mole. We do that multiplying. Moles cancel out. Now we get the value we need, 58.8 grams. What is the molality of a solution where 20.0 grams of sodium chloride are dissolved in 2.00 kilograms of water? So we determine the molar mass of sodium chloride. It is 58.44 grams per mole. We divide that into the mass, 20.0 grams. We see grams cancel out. We have moles. And then we divide that by the kilograms of the water. And we get 0.171 molal. We can write that as a little m. We can write the word molal out, or we can write moles per kilogram. Calculate the mole fraction of glucose and of water in a solution where 120 grams of glucose, we see what that is, C6H12O6, are dissolved in 250 grams of water. So we have our equation. The mole fraction of the glucose is the moles of glucose divided by the moles of glucose plus the moles of water. So we have to get the moles of the glucose, so we take the 120 grams divided by the molar mass, and we get 0.666 moles of glucose. We need the moles of water, so we take the 250 grams of water, we divide by the molar mass of water, 18.02 grams per mole, and we get 13.9 moles of water. So for the mole fraction of glucose, we take our 0.666 moles and divide it by 0.666 moles plus 13.9 moles and get 0.0457. The mole fraction of the water is 1 minus the mole fraction of glucose, 1 minus 0.0457 equaling to 0.9543. Calculate the mass percent glucose in the glucose solution from above. So we take the mass of glucose, 120 grams. We divide it by the mass of the glucose, 120 grams, plus the mass of water, 250 grams, times 100. We get 32.4% glucose by mass. There's an example problem for you to come back to. So our next section is factors affecting solubility. We have several factors we will talk about. The first one is properties of the solute and solvent. And basically we will end up with like dissolves like. So we will consider the three processes involved in dissolving and their associated energies. In our diagram, we have the solute that has to be separated to the individual separate solute molecules. That's referred to here as the expanded solute. That's step one. The energy associated with that is delta H1. It takes energy to pull the solute particles apart from each other, so that's an endothermic process. We're overcoming the intermolecular forces between the solute particles, or the ionic bonds, whatever they happen to be, depending on what kind of a solute we're dissolving. We also have to separate the solvent particles from each other. That is step two. Delta H2 describes the energy it takes. That's also an endothermic process. So we're overcoming whatever kind of attractions there are between the solvent particles. Then, when the solute and the solvent come together, they might, if they can favorably interact, give off energy. The delta H3 is the term that describes this step, step 3, and that's the interaction between the two. That step often gives off energy. It's often exothermic. Okay, so the delta H of the solution, what it takes to cause the solute and the solvent to mix together, is delta H1 plus delta H2 plus delta H3. In this diagram, we see that we have energy versus time, and we have the energy of the separated solute and solvent particles. The energy it takes for that to occur is delta H1 plus delta H2, so that always takes energy. So we climb upward on our energy axis. Then, when they mix together, let's say energy is given off, so we'll have a downward arrow. If a lot of energy is given off, if the delta H3 downward arrow is much bigger than the sum of the delta H1 and delta H2 upward arrow, then we have definitely this being an exothermic process. The delta H of the solution, that downward green arrow, is going to be something less than 0. So exothermic, that mixing, that dissolving of the solute in the solvent would definitely happen. If, on the other hand, we have delta H1 plus delta H2, so energy climbing upward, but then we only have a small delta H3, so now we're looking at the second energy diagram, then, and that delta H3 downward arrow is smaller than the yellow upward arrow, then we have a delta H of the solution that's endothermic, something greater than 0. So, summarizing, if delta H of the solution is less than 0, that is, the dissolving is exothermic, then a solution forms, that mixing happens. If delta H of the solution is greater than 0, then the dissolving is endothermic, but is a small value, then a solution can form because there's enough energy in the surroundings to supply that small value. And that would happen because the disorder of the universe, remember our two system and surroundings and universe terms, the disorder of the overall process, the universe, increases in the dissolving process. So the disorder, the chaoticness, increases in the dissolving process. And processes naturally move toward a more disordered state. For example, in A, we have spheres separated. It's spheres before the partition is opened. In B, here's what the spheres look like after the partition has opened. The spheres naturally mix. Processes naturally go in the direction that leads to the most probable state. That's basically probability arguments saying that. This is the mixed state because there are so many more ways of placing the spheres to give a mixed state than the unmixed state. We spend a lot of time discussing this topic in chemistry too. But basically, if the delta H of the solution is small, that is a small positive number, the dissolving will still happen because of the favorability of the mixing itself, the higher state of disorder it gives rise to. All right, so a way to summarize this. Delta H of the solution is, as we said before, delta H1 plus delta H2 plus delta H3. We're going to consider several different solute-solvent possibilities. We'll consider polar and nonpolar. So if we have a polar solute and a polar solvent, then delta H1, which is always endothermic, is going to be a large number because those polar molecules like each other. They're not going to easily separate. Well, polar solvent, we also have a large delta H2 because, again, they don't want to separate. It takes a fair amount of energy to do so. But when they mix together, both being polar, that's favorable, they like each other, and they will give off a lot of energy. So delta H3 can compensate for the delta H1 and delta H2. And so delta H of the solution is a small positive number. It's a small positive or negative number. Well, it's a small positive, or maybe it's even a large negative. If negative of large or small, that will happen. If positive but small, then the dissolving will happen. So yes, a solution would form. If the solute is nonpolar, delta H1 is small, but if the solvent is polar, delta H2 is large. Now, polar and nonpolar don't mix well, so delta H3 is small. It doesn't compensate for the large delta H2, so we end up with a large positive delta H of the solution, and a solution does not form. If the solute is polar, delta H1 is large. If the solvent is nonpolar, delta H2 is small. But being polar or nonpolar, delta H3 is small. It cannot compensate for the large delta H1, so we end up with a large positive delta H of the solution, and again, a solution will not form. The last possibility is if they are both nonpolar, delta H1 and delta H2 would be small. And then delta H3, well, nonpolar likes nonpolar, so they'll mix well together. And we will end up with a small positive or negative delta H of solution. So yes, dissolving will happen. And what this comes down to is like dissolves like, polar dissolves in polar, nonpolar dissolves in nonpolar. Okay, so that's one of our factors that affects solubility. The next one we'll talk about is pressure. Pressure has very little effect on the solubilities of solid or liquid solutes dissolved in a liquid solvent. But pressure does have a big effect on gaseous solutes dissolved in liquid solvents. The greater the pressure of the gas above the liquid, the greater the amount of dissolved gas in the liquid. Now, is the pressure above the liquid in a can of soda large? Well, before opening it, we don't know, but once we open it, we get that very much fizzing occurring as soon as we pop it open. And that's due to the large amount of CO2, that headspace of about 5 atmospheres, and the CO2 that's within the liquid that is coming out, pushing some of the liquid above it out, and that's why we have all that fizzing going on. It's due to the escaping CO2 gas. The concentration of dissolved gas in the liquid is given by Henry's law, which is the concentration C of the dissolved gas is equal to K, a constant that is characteristic of the solution, times P, where P is the partial pressure of the gaseous solute above the liquid. Here's an example. The pressure of CO2 gas above the liquid in a soda, in an unopened can of soda, is 5.0 atmospheres. What is the concentration of dissolved CO2 in the soda? And the constant is, for the CO2 dissolved in water, 0.031 moles per liter atmosphere. So we have C is equal to Kp. C is equal to 0.031 moles per liter atmosphere over 5.0 atmosphere, and we end up with 0.16 moles per liter, or 0.16 molar. If we increase the pressure above the liquid, then we could get even more dissolved CO2 in the liquid. Of course, we'd have to increase the pressure of CO2 above the liquid. Here's an example for you to look at later. Okay, the next factor that we will talk about that affects the solubility of a solute in a solvent is temperature. We'll first look at solid solutes dissolved in water, and we see a graph of solubility versus temperature. For sugar, we see that it increases as temperature goes up. The same is true for potassium nitrate and sodium nitrate and sodium bromide and potassium bromide and potassium chloride, the blue graphs. But notice that for sodium sulfate and cerium sulfate, the red lines, their values go down a little bit as temperature goes up. So what we have is the solubilities of most ionic and molecular solids. We have all ionic solids except for the sugar, that's a molecular one. They become more soluble as temperature increases. So for most solutes, they become more soluble as temperature increases. But there are exceptions, so we see the two there as exceptions. Lithium sulfate is also an exception. It's not shown, but they become less soluble. In general, dissolving occurs more quickly at high temperatures, but it does not affect overall solubility. That is the more, but no, let me say that correctly. In general, dissolving occurs more quickly at high temperatures, but how quickly it dissolves does not affect the overall solubility. That depends upon the nature of the particular solid solute. Okay, so that's solid solutes in water. Gaseous solutes in water, as we can see from solubility versus temperature, they become less soluble as temperature increases. And I think that you know that from personal experience. If you have a leftover carbonated drink like beer or like champagne or like soda, and you don't want it to go flat too quickly, you would store it in the refrigerator. Cooler temperature, it can hold more of this dissolved CO2 in it. Here's an article that I think you might enjoy. Come back to it and take a look at it. It's on a tragedy that occurred in 1986 that I think you'd find interesting given what we've talked about and the temperature and pressure effects of solute dissolved in solvent. Okay, our next section is called colligative properties. Liquid solutions have physical properties that are significantly different from those of the pure solvent. So we have a solvent, it has certain properties, certain boiling point, certain freezing point, certain vapor pressure. When we put some solute into it, we have a solution, and we find that those properties, the vapor pressure, the boiling point, the freezing point, are very affected, are very different from what they were as in the pure solvent. These properties depend only on the amount of the solute, which has to be non-volatile particles, and not on the actual identity of those particles. So whether it be sodium chloride or potassium bromide, it just matters how much of those we have in there and not what exact solute we have. A non-volatile solute, so that would be one that does not readily evaporate, it causes the vapor pressure of the solution to decrease, the boiling point of the solution to increase, and that's called boiling point elevation, the freezing point of the solution to decrease. That's called freezing point depression, and it causes osmosis to occur. Okay, so in comparison to the pure solvent, the solution causes the vapor pressure to decrease, the boiling point to increase, the freezing point to decrease, and we can get osmosis. Okay, so we will look at each one of those. So first, the vapor pressure. What we have in this diagram is water, pure water in a sealed container, and at a temperature of 20 degrees Celsius, the vapor pressure would be 17.5 torr. Now, when we dissolve some glucose in it, we see that the vapor pressure goes down a bit. If we dissolve enough glucose so that our molarity of our solution is 2.97 molar, we see the vapor pressure drops to 16.6 torr. Notice that we have, in our last column there, we have 2.97 molar ethylene glycol. Same molarity and same vapor pressure. So this would be like the colligative property we talked about earlier. It doesn't matter the identity of the solute, it just matters the amount. In our case, the 2.97 molar. We get the same effect. Non-volatile solutes lower the vapor pressure of a solution. And this effect is given by Raoult's law, which is the pressure, the vapor pressure, the pressure of the solution is equal to the mole fraction of the solvent times the pressure, the vapor pressure of the pure solvent. So the mole fraction is something less than 1. So the pressure of the solution is going to be something a little less than the pressure of the pure solvent. So we have P of the solution is the vapor pressure of the solution. The mole fraction of the solvent is the moles of solvent divided by the moles of solvent plus moles of solute. And P of the solvent is the vapor pressure of the pure solvent. Okay. Example. What is the mole fraction of water when we have sodium chloride dissolved in water? Realize that 1 mole of sodium chloride makes for 2 moles of particles. It makes for a mole of sodium ions and a mole of chloride ions, and what matters is the total number of particles, so that gives us a total of 2 moles of particles per 1 mole of the NaCl. Okay, so we have the mole fraction of the solvent, the one we're after, the mole fraction of the water, is the moles of the solvent divided by the moles of the solvent plus the moles of the solute. So specifically, we have the mole fraction of water equals moles of water over moles of water plus moles of NaCl. So as we talked about, 1 mole of NaCl makes for 2 moles of particles. So what we have is the mole fraction of the water is the moles of water over the moles of water plus the moles of the sodium ions plus the moles of the chloride ions. So we have to remember to take that into account with an ionic compound. So here's an example. What is the vapor pressure of the solution if 31 grams of NaCl are dissolved in 220 grams of water at 40 degrees Celsius? We're given the vapor pressure of water to be 55 torr at 40 degrees Celsius. Alrighty, so we figure out the moles of water, 220 grams divided by the 18.02 grams per mole, the molar mass of water. That's equal to 12.21 moles of water. The mole fraction of the sodium chloride is 31 grams divided by its molar mass, 58.44 grams per mole. So we have 0.530 moles of NaCl. Alrighty, now the mole fraction of the water is the moles of water over the moles of water plus the moles of sodium plus the moles of chloride ions. So we have 12.21 moles over 12.21 moles plus the amount of sodium in sodium chloride is 0.530 moles. The amount of chloride ions in there is 0.530 moles, so we get the mole fraction to be 0.920. Now we have the pressure of the solution is the mole fraction of the solvent times the mole fraction, or times the pressure of the solvent. So we have 0.920 times 55 torr equaling 51 torr. So it has definitely dropped down. The next property that we'll talk about that is affected by the presence of the non-volatile solute is boiling point elevation. So here's the phase diagram, which is pressure versus temperature for water. And we have it for pure water, that's the red lines, and we have it for a mixture, a solution, an aqueous solution, that's the blue lines. So as we talked about, the vapor pressure is lower. So at a given temperature, the blue line is always lower than the red line. You have to make those vertical drops going from the red to the blue at a particular temperature. So the boiling point of the pure water, actually at 1 atmosphere, it would be drop straight down from the red. You get the left side of that delta T sub B. The boiling point of the boiling point of the solution is drop down from the blue line because we are at that 1 atmospheric pressure. So that would be the boiling point of the solution. It's higher than that of the pure one. Okay, so as a reminder, to boil a liquid at an atmospheric pressure of 1 atmosphere, the liquid's vapor pressure must equal 1 atmosphere. For pure water, this occurs at a lower temperature due to the greater vapor pressure of pure water than it does for the solution, since the solution must be at a higher temperature in order to have a vapor pressure of 1 atmosphere. The difference between these temperatures is delta T sub B. And a value for delta T sub B is given by this boiling point elevation equation. Delta T sub B, which describes how much it goes up by, is equal to I times K sub B times M. So delta T sub B is the boiling point elevation. I is a factor called the Van't Hoff factor. It's unitless, and what it has to do with is in a mole of solute, how many moles does it break down to? So in 1 mole of NaCl, we have 2 moles of particles. I would be 2. In 1 mole of CaCl2, we would have 3 particles. I would be 3. With any molecular solid, 1 mole of molecular solid equals 1 mole of particles. So I would be 1. K sub B is the boiling point elevation constant. It depends on the solvent. So we have in the table there The second number column would represent the boiling point elevation constant for different solvents, for water and so forth. M is the molality of the solute in the solution. So here's an example. Calculate the boiling point of a 1.0 molal aqueous glucose solution. So we use delta T sub B equals I times Kb times M, where we're talking about a molecular solid, so I is 1. K sub B, we go to our table, and for water we see the value 0.51. The units given in the table are degrees Celsius, kilograms per mole, and then the molality is 1.0 moles per kilogram. Unit analysis shows us that moles and kilograms cancel out, so we're left with just degrees Celsius. So delta T sub B is 0.51 degrees Celsius. The boiling point of water is 100 degrees. It's going up by this 0.51, so our boiling point that we're after is 100.51 degrees Celsius. Freezing point depression is the next colligative property that is affected, that happens because of the presence of a non-volatile solute. Here's the phase diagram again for water. And according to the graph, we have the red lines again representing pure water, the blue lines representing the solution, and the freezing point of the solution occurs at a lower temperature than that of the pure water. This difference is delta T sub F. So kind of like the boiling point elevation, we have a very similar equation. Delta T sub F equals I, K sub F, M. So delta T sub F is the freezing point depression. I is that same Van't Hoff factor. K sub F is the freezing point elevation constant. It's given in the last column of that table and depends on the solvent. M is again the molality of the solute. Okay, here's an example. Calculate the freezing point of a 1.0 molar, of that same one we worked with before, 1.0 molar aqueous glucose solution. So we have that delta T sub F equation. We put I to be 1. Now in our table we find K sub F to be 1.86 degrees Celsius kilogram per mole. That's the value for water. We see it by looking at our table. Water sliding over to K sub F, 1.86, attaching the units. We multiply by the 1.0 moles per kilogram. We get delta T sub F to be 1.86 degrees Celsius. Okay, so that's the amount that the temperature goes down by. Well, water freezes at 0 degrees Celsius, so the freezing point, so not BP, it should say FP. The freezing point is 0 minus 1.86 or negative 1.86 degrees Celsius. Notice that it goes down much more than it goes up. So the freezing point depression is greater than the boiling point elevation. So here we have freezing points of water, glucose, KCl, and CaCl2. So the freezing point of pure water, 0 degrees Celsius. Of 1 molar glucose, we calculated to be negative 1.86. If we had instead had 1 molar KCl, we end up with the equivalent of 2 molal particles, and so the freezing point is even greater. The freezing point depression, 3.72. due to I being 2. And it's lowered even more if we have calcium chloride because of I being 3 there. Delta T sub F can be used to determine the molar mass of an unknown solute. Example, the addition of 0.24 grams of a molecular solid of sulfur, So it's Sx to 0.100 kilograms of CCl4 liquid. That's the solvent. The sulfur, the Sx compound, is the solute, lowered its freezing point by 0.28 degrees Celsius. Calculate the molar mass and the value of X of the solute. K sub F for the CCl4 is 30 degrees Celsius kilogram per mole. Alrighty, so what we have is 0.24 grams of this molecular sulfur solid that was dissolved in 0.100 kilograms of CCl4. The freezing point went down by 0.28 degrees Celsius. That is delta T sub F. And we want to find the molar mass of Sx and the value of X. Okay, so the molar mass, looking at the second column, the molar mass is grams of Sx per mole of Sx. We know the grams of it to be 0.24, but we don't at the moment know the moles. But we do have other information, and it's a freezing point type problem. So let's look at delta T sub F equals I K sub F times M. Now, we have delta T sub F, that's 0.28. I, it's a molecular solid, so I is 1. K sub F, we have 30 degrees Celsius kilograms per mole. So we can calculate the molality, and the molality involves moles. So let's do that. So we solve for M, that's delta T sub F over I K sub F. We have 0.28 degrees Celsius over 1 over 30 degrees Celsius kilograms per mole. Our units come out to be moles per kilogram, and the number is 0.0093. So we have the molality is 0.0093 moles Sx per kilogram of CCl4. Now, we want to get rid of that kilogram CCl4. So how do we do that? We multiply by the kilograms of the CCl4 that we're using in the problem. So we have 0.100 kilograms times 0.0093 moles per kilogram. The kilogram units cancel, and we get 0.00093 moles of Sx. Now we can put that into our molar mass equation. So we have 0.24 grams divided by 0.00093 moles, and we calculate the molar mass to be 257 grams per mole. And to find the value of X, what we do is we take this mass, that's of our complete compound, divided by the molar mass of just a sulfur. So 257 grams per mole over 32 grams per mole, that equals 8. That means that our compound must be S8. X is 8. Our last colligative property is osmosis. Osmosis is the tendency of the solvent to flow through a semi-permeable membrane to a more concentrated solution. And osmosis occurs because of the presence of the non-volatile solute. Okay, what we have is, in the diagram on the left, we have a U-tube that has a semi-permeable membrane right down at the bottom. We have pure solvent on the left side, and we have a solution on the right side. So a pure solvent and its solution containing a non-volatile solute are separated by a semi-permeable membrane through which the solvent molecules, the blue ones, can pass, but the solute molecules, the green ones, cannot. The rate of solvent transfer is greater from solvent to solution than from solution to solvent. So the solvent, the blue ones, on the blue side, the blue particles can go through the membrane more easily than the blue particles on the green side can go. So the blue can travel toward the right more easily than the blue can travel toward the left. What that does is it causes the liquid level in the green side to rise. The system at equilibrium, that would be diagram B, where the rate of solvent transfer is the same now in both directions. So it's reached equilibrium. The rates of the two sides are now equal, but the liquid level on the right side has risen. Basically, osmosis happens because the solvent solution, it's like you can think of it as a tendency of the solution to, by the solvent, try to become more diluted. And our next diagram is the normal flow of the solvent into the solution, that is osmosis, can be prevented by applying an external pressure to the solution. The minimum pressure required to stop osmosis is equal to what we call the osmotic pressure of the solution. So back up in our diagram here, this first one, we see that the solution level is higher than the solvent level. That difference in height is due to the solvent traveling more easily in the one direction, in the direction toward the more concentrated solution, and that process can be stopped by applying pressure on the more concentrated solution side. And that pressure is called the osmotic pressure. The osmotic pressure equation is the pressure, which is given by the capital pi, Greek symbol pi. So the osmotic pressure in atmospheres is equal to I, that same Van't Hoff factor, times m, the molarity of the solute in the solution, times R, the ideal gas constant, where we're using the value 0.08206 liters atmospheres per mole Kelvin, times the temperature in Kelvin. So here's an example. What is the osmotic pressure of a 0.010 molar sucrose solution at 25 degrees Celsius? Okay, so we have our equation. Pressure equals ImRT. I is 1 for this molecular solid, sucrose, times 0.010 moles per liter times R, times 298 Kelvin, 25 degrees Celsius. And we end up with units, except for atmospheres, canceling out, and the number is 0.24 atmospheres. Okay, so read through chapter 11 in your textbook, do the assigned homework problems. You will do an activity on this soon and get more practice working with colligative properties and solution concentrations. And when the quiz is open, be sure to take the quiz.